For here is it? 19. Are you sure? Yes?
Yes, sure.
How many treatments we have?
Three.
How many treatments we have?
Four.
We have 4 treatments. So you want to change your mind?
No.
Still 19. Anybody else? You have 4 treatments? No, this should be 3.
Oh, why 3?
Oh, -1.
No.
No. Lawrence, yes, how many? Oh, the last one, this one. Total just now was what? 4 times 5 equals? This is the total. So what should be the degree of freedom? Now you should put 19 here. Yes, it's total. 19 is down here, not from there. So to find this answer, it's just this minus this. And this is what? This plus this equal this. One. We have 1 here minus 1. So this one is formula. I don't want to go through formula. So one way and over. One way only. When we go to CRD, we will have 2 things here. I mean RCPD. We will have 2. So they call it 2-way and over. Lukman. Yes, Lukman. Can you tell us for this experiment how many treatments we have? 4. Because here they have 3. So that means there are 4 treatments. 4 minus 1 equals 3. How many replications? Lukman, choose somebody. 1. How many replications we have? Okay. Are you sure?
Yes.
Do you agree? You say we have 5 replications, right? Okay. You say we have 5 replications. Just now, how many treatments, Lukman? 4. And then you say we have 5 replications, right? What times 5 equals?
20.
20. Is it okay here?
No.
So it should be 4. 16. And then this is correct. We can tell. Okay, in this table, you need data to get all of these things, but we want to do something here so that you can understand what is operating in this table. After we will do example how to do the calculation. So once you do your sum of squares, you will get this answer. And then also do total sum of squares, you get this answer. To get this answer, you just, this one minus this number will give you this answer. Please remember, to get this answer, this error, it's always this one minus this one, or this one minus this one. That is the shortest calculation to do. For example, 15 minus 3 equals 12. 114.35 minus 80.92. Can you find the answer using your calculator? See this answer? 114.35 minus 80.92 equals what? 3.43. Another way around. If you add this and this, you will get this answer because it is total. Clear? Anybody not clear? This is your chance, to say I'm not sure what you are talking about. How do you get this? Do you remember? How do you get this 26.97? This divided by 3 will give you this answer. This number divided by 3 will give you this answer. 80.92 divided by 3 equals? Calculator. 80.92 divided by 3.
26.25.
Okay, same thing here. 33.43 divided by 12 will give you this answer.
Yeah.
Okay. This last number is this divided by this. We give you this answer. So 26.97 divided by this will give you this answer. So is the answer significant? Is this significant? How do we tell whether this F calculated, we can reject or accept our null hypothesis for the treatment? How do you tell? You have to use F table, right? Remember F table. The easiest way I always tell students do like this. Then you find your F table. In your F table, you must find one answer. Put your critical point. Do you have the table? How do you look at the table? How do you find the answer from the table?
We have no table. We don't have chair.
How do you find the answer from the table? In the table, we have numbers like this. We have numbers here, and then we have numbers here. And then in here, we have many numbers. And of course, they will tell you here whether it's 5% or 0.05 or 1%, 0.01. So it depends on which level of significance you want to do. You want to be very perfect, you must go 1%. In agriculture, we allow 5 to 10% mistake. In medicine, they allow 0.001%. Because if you make mistake, you can kill people. They don't allow you error. In agriculture, we allow maybe 5%. You can use 5% probability. So you can see here, they have this number 3 and 12. Here, degree of freedom 3 and 12. So you have to look for 3 here and 12 here. And then find the answer in the table. Let's say 3 and 12 reach here. You find the answer. For you to be able to write here, I think they found the answer to be what? 3.49. If you look at the table, the answer is 3.49. This number here, 3.49. For 5%, huh? 1% will be different. Okay. So once you know this number, then you can compare with this one. Your F calculated. Now, is it outside or inside? 9.68. Is it outside or inside there?
Outside.
Yeah, it's somewhere here, right? So reject or accept?
Reject.
You reject. You reject what? HO. You reject HO and you accept H. Okay. Is that clear? So why do we use 3 and 12 and not 12 and 15? Why we use 3 and 12? Here, 3, 12. Not 3 and 15 or 12 and 15. Huh? Yeah, because to get this answer, this divided by this. We use the number from here. The simple way to explain to you, there are reasons they do so. But you use these two numbers to get this answer, and the degree of freedom here is 3 and 12. So we compare the degree of freedom from the table as well. 3 and 12, we have to match these two numbers. Because here they use, to calculate this answer, they use these two numbers. And this one corresponds to 3, and this one corresponds to 12. Okay, you can see here, 26.97, right? Divided by 2.79 equals what? 9.68. This is your numerator, right? And this is your denominator. So that's why in the F table they will put here degree of freedom for numerator, degree of freedom for denominator. Don't 12 and 3 cannot. Should be 3 and 12. Okay. So So this is your guide to know what to look for. These 3 and 12. Because in the table you have to look for the numbers only. You have the table? I put already in either 2 types of table. So are we clear? Okay, right. Another table here. Who was it just now? Choose somebody. Yeah. In this experiment. Okay.
How many treatment?
Don't be a robot. I already took the thing around. I put total on top. Huh? Live treatment. Are you there? Yes. That's all. Is there? So which then you want? Oh. Okay, correct? Is it correct? You said treatment is 5. Okay. Here the treatment is the type of soil. So correct, it's 5. Because we have 4 here. 5 minus 1 is 4. Okay. Then Tawaf, please choose somebody. Don't think too much. Sirida. Rida? Huh? Riza. Rija. Okay. Okay. He says Si Rija. Si Rija means sister Rija. Si Rija, how many total experimental units we have? 20. Correct? 20? Okay. Si Rija, please choose somebody. Huh? Magdalene? Okay, Magdalene, how many replication do we have for this experiment? How many replication? How many replication? You have to do some work, to find replication. Magdalene, try. How many replication? We have treatments here 5. Total is 20. How many replication? 4. Huh? 4.
Kan suruh treatment kah yang
5 times 4 equals
20.
20, right?
5 treatment lah.
Are you clear?
5 replicate treatment.
So there are only 4 replication here. Okay. Of course, here you can see one way ANOVA, same thing. They only show F for this one. Our treatment is one way ANOVA. Okay. So when they put this two star here, if you read the literature and then you see 2 star, 2 star usually mean 1% significant. It's highly significant. That's 1%. Okay. Okay, you can see here significant level at 1%. If 1 star means significant at 10%. Oh no, 5%. Okay. If no star means no significant. You have to accept your hypothesis. There are no differences. So if you want to check the table, okay, Magdalene, choose somebody.
Izam.
Okay, if you want to look your F table to find what is the F for table, to find this answer, what is your numerator and denominator? What do you look for horizontally and vertically? Which number? Do you look for here and here? Which numbers? In the table, you have to look right. You have to choose one number here and one number here. The top is 4, okay. And then other side, horizontal, vertical, 15, correct? So you have to look for 4 and 15. Please don't look for 4 and 19. Wrong. It should be 450. If you I'm saying if you look for 19, it is wrong. Okay, clear? You can see here, I already write this here for you to remember. 5% for 15. Okay. So 3.06, this is one lot, 3.06, 3.06. Then F calculated is 11.18, which is somewhere here, 11. So, reject. We reject. We reject the null hypothesis. Okay. So usually, when after you finish all your experiments, they will ask you to do something else after your result, maybe to show the means of your soil types. You see here 5 soil types, they have the mean yield. Sometimes you can see here replication is not the same. They didn't do equal replication here. Right? And they show the standard error. This one we are not going to do in this course. We should have done in biometry how to calculate standard error or this one. We are not doing in this course. And then of course your coefficient of variation here. You can see CV is 18.1%. How accurate is this experiment? Experiment, of course, we will have error. Usually we have error. But in agriculture, we are around maximum up to 20% your coefficient of variation. If your CV is very high, means your experiment is lousy. You did not do a good job. Or there is too much variation. Your answer is not reliable. You have to repeat your experiment. So you must try to minimize this one. You cannot get 0, impossible. But try to minimize as best as possible. So people can test and see whether your coefficient of variation is very high. I don't want to read this paper, this lousy experiment. But sometimes it can happen, but you need to know how to do analysis of your data. Sometimes when you start your experiment, there are certain cases, when you start your experiment, you start with materials which are not the same. Let's say your seedlings are different size or different type of material. So this is the one you need to juggle, before you start your experiment. Start with equal footing. Everything is the same variety, same age, same type of plant. But if the situation arises where you cannot have this kind of situation because of maybe certain reasons, you cannot get the same plant type, you have to start with something different. There is another way where you can do your analysis. It's called analysis of covariance. ANCOVA. You have to analyze your data using different methods. It's called ANCOVA. So this ANCOVA here means covariance. Analysis of covariance. That means you to take account of what happened before. That means you don't start with the same material. So if that happened to you, please make sure you use analysis of covariance. When I was in UPM, we have one student from Iran. She is collecting data about crabs. You know crab? You have to go to the field very early in the morning to the seaside to collect ketam. And very difficult to catch the ketam to get the same size. Every time goes, sometimes cannot find anything. Sometimes cannot find. Today find, tomorrow cannot find. So the ones you find is very precious. And then not the same size. You don't know their age. You don't know what is happening to this ketam because you did not breed them. You just find them in the field. So, how to do this one? To do the analysis. Okay. Money. Is it money? The bags there, is it money? If the bag contains money, which one you want? Number one. Oh, very smart. So, say number one. this is full of gold. Which one do you want? Which bag? Huh? If full of gold, you want number 4? Ah, say one number 4, not number 1. What is matter?
Habis.
The bags are full of gold. Number 1 or number 4? You see? Oh, very sharp. You see number 4. Are they different? This is what we deal with in statistics. Are they different? They look different, but are they statistically different? The only way you can tell whether, of course, when we see like this, they are different, of course, in terms of size or what you see on the picture. But in terms of statistics, you need to do statistical analysis. And the way to test is called, maybe you have come across post hoc test. Post hoc. So to tell whether this is really different from this one or this is really the same as this one, we need to do post hoc test. That is what happened after ANOVA, post hoc. For example, we do LSD test. Have you heard of LSD? Tukey test. Have you heard of Tukey test? Never mind, we will do these things. Maybe we need to. Okay, it's okay. My student also eventually need to. So we will find, if you see the literature, usually when they put the mean, they will put a number, a letter beside the mean. A, B, C, A, B, B, D, for example. So when you see these letters against the mean, maybe 32.5, 36.7, 38.9, this is the mean, mean. Let's say the mean height. Then they will put these letters here. This letter is to tell you whether this is different from this one, statistically. Are they significantly different? If the letter is the same, means no significant difference. If you have the same letter, means we are the same. So which one is the same here? 31.7. Maybe 36, 38.9. Which one are the same here? 32.5, and these two are the same because they have the same letter. B and C different. A and B different. B and C. But these two are the same. They are not different. These two. This B here, this one, is also the same as this one. So they will attach a letter there to tell you whether there is difference. And this is called a post hoc test. I will not ask you to do this by hand because the software will do for you. The only thing you must know what it means. Okay. Okay, done for this topic. Let's take a break. 5 minutes. 5 minutes break. Any question? Try to do by yourself, step by step. I give you examples, step by step. 1, 2, 3. Is a step by step example. Last time is CRD, now is RCPD. So usually RCPD we will do what we call two-way ANOVA. Two-way ANOVA. Randomize, also randomize. You have to randomize completely, but we need one more thing here. We include what we call a block. Block. Why do we block? Because of certain reason. We want to minimize the variation between the treatments. Block. Let's say I have a field here. This field is high fertility, this section. The soil here is high fertility. And then this side of the field is low fertility. Or this side of the field is what we call poor drainage. Poor drainage means the soil is holding a lot of water, easy to get banjir. Here is high drainage, or good, better I say good drainage. Easy for water to go through the soil. So as we go here, the drainage become wet and bad, not so good. Here, as we move this way, the fertility become reduced and reduced. We know from the field. So because of this, if we want to do an experiment using this whole area, we need to do blocking. We have to block. So in this case, we will block like this. Please don't block like this. If this is your block, you have not solved any problem because there is variation along. You cannot block this way. I mean, don't put a block like this. No. You have to block this way. Maybe 3 blocks or 4 blocks. Okay. As long as you block perpendicular. Means when we block like this, we know all this area is high fertility. They are the same condition. Or here, if we are talking about drainage, all this section is poor drainage. And then as we move along, we come here, this one block, all either low fertility or good drainage. Understood what I'm trying to say? We are trying to make the condition the same. We are minimizing what happened in the field. Because this, we don't want it to affect our treatment. We can control our treatment. But this way, nothing we can do, only is to do blocking. By blocking means we make sure the conditions within the block are the same. So if we have 4 blocks here, block 1, block 2, block 3, and block 4, and then we have 4 treatments. How many experimental units? Okay. 4 treatment per block. How many experimental units? 6, right? 4 times 4 equals 6. So we have 4 blocks. 4 blocks times 4 treatments. This block is usually considered as the replication. Is considered as the replication. The block experiment, the block is considered the replicate. So where do we randomize? Here, because we already blocked, we have some restriction. You cannot randomize everywhere. Okay? So here we have 4 treatments. You must have your A, B, C, D here, inside here. Here also you must have A, B, C, D. Block 3 you must also have A, B, C, D. Block 4 you must also have A, B, C, D. But is this correct? What is wrong with this one?
Not random.
Not random. So you have to randomize. Make sure all your treatments are in the block, but you randomize. Remember the pictures I showed you about the chicken? Same thing here. All your treatments are here, must randomize. All treatments are here, we have to randomize. So you randomize based on each block. Clear?
Yeah.
Okay, right. So same thing here, we will do this thing and later we will do Excel. This is the only thing we can do with Excel, which is easy, block and CRD. If you want to do split floor, Latin square, factorial, not advisable to use Excel. You have to use SAS or SPSS. Okay? Use SAS or SPSS or other software that is available there. So in UMS, we have license for SPSS. So learn how to use SPSS. If you want to do SAS, I can teach you because if you go to places like Marti or Jabatan Britania, maybe you end up working there, you might not find SPSS, you might only find SAS. So it's good to learn how to use the SAS as well. So in this design, you can see here, treatments are assigned to blocks consisting of the experimental units. Block 1, block 2, block 3, block 4. Each block has the experimental units. Okay. Why a block? Why block is that? To keep variability among experimental units within the block as small as possible. So between these blocks here, we make sure the variation is minimized. Means we know that here is all high fertility. Here we know is all low fertility. We try to make sure that things are in the same environment. Okay, and then we maximize differences among the block. You can see here, this one high fertility, this is no fertility. They are different. Like blocking. In your hostel we have female block and male block, right? So different blocking. Okay. So note here that there is no contribution to precision in ANOVA of treatment differences if there is no block difference. If you don't need to, what this is trying to tell you, if your condition is the same everywhere, no need to block. Don't waste your time to block. Unless you have this kind of condition where things are different, then you need to block. Otherwise, just use CRD, the simple design. Okay, when to use, you can see suitable for field experiment. Usually we don't use this in the lab, unless of course you are working in a big lab, maybe one side got light, another side no light, one side is cold, another side is warm. So suitable for field experiments where the number of treatment is not large, and the experimental size are predictable productivity gradient. We can predict here high, low fertility, poor drainage, good drainage. We must be able to block experimental unit in some way. So you must know the reason why you block. Don't just block because you like block. You must have a reason why you block. Okay. Each block must be large enough to accommodate all treatments. So each block, when you block, each block must have all your treatments. A, B, C, D, A, B, C, D here, A, B, C, D, A, B, C, D. Yeah? So we can be able to do two-way ANOVA. Why two-way? Let's do this one. Two-way. Now we go to what we call two-way analysis of variance. Okay. One way, we have borrows. In two-way, we have here, one more, another one here, one there, another one. Okay. You can see here in one way we have, let's say this is your source of variation. We have treatment, error, right? And total. Only one way. Whereas in two-way here we have our source of variation, we have treatment, and then we have one more block. Or some people will put here a replication. And then error. And total. So we have one more. 1, 2, 3, 4. Here, 1, 2, 3. The additional is this one. So we will have two things to look at here. This one we only look at this one. So we want to tell whether there is a difference between the block and also difference between the treatment. That's why it's called two-way. Okay. In some cases, which I think you will not encounter, you will not get to do this. There can be one more thing here in the middle here. Block times treatment interaction, then error and total. But most of the time, I don't think you will come across this. This will happen if you have replication within the block. That means within, let's say, block A, just now we have only 4. If you replicate those treatments many times within one block, then you will have that condition. I think most of the time you will not do it. Unless you do master's lab or PhD. Or your supervisor wants you to do it. Then okay. No choice. Okay, when collecting data, especially in the field, today I come and do block 1. Tomorrow, my last student, I stop today, I do block 2 tomorrow. Then the next day, I do block 3. You can do this, can be done. Let's say your field is maybe 20 hectares, like in your farm estate, any big, you are collecting data. You can do so, but make sure you are consistent. Anytime you collect data, you must do one first one day, the next day another one. Don't decide to do all the same day the next time you collect data. No. So if you started off collecting data all the same day, the next time you want to collect data, maybe 1 month or 1 week after, you must do all your data collection on the same day. Or if you have decided, okay, this first data collection, I want to measure the yield of the plant. Monday, I do block 1. Tuesday, I do block 2. Wednesday, I do block 3. Next time you want to do so, collecting data, you must follow the same sequence. So there's a regular pattern. Otherwise, you will increase your error, which we don't want to happen. Yeah? And make sure it's the same person collecting data all the time. You must have the same person collecting the data. Don't today you collect data, tomorrow you ask your friend to do. Don't do it. Your friend maybe do in charge of, don't care. Just right answer only. That is one. Or the way you see things, the way one person sees something is not the way another person sees.
Yes.
Maybe you want to collect maybe the color of the fruit. Based on the color of the fruit, you're taking data. This person may be colorblind. See, green is red. So you must have the same person collecting data. Even to weigh liquid, to measure liquid. One person, the way they measure is not the same as the other person. One person might always make mistake, 1 drop extra, because maybe nervous or cannot see the meniscus properly. So try to be the message here is be consistent. We try to be consistent. Yeah? You can see this thing here. Any problem here? I have a field. What is this?
House.
House?
The
This one is what? Alright. This one is what?
Way. Path.
If I want to do experiment here,
Path.
you can see, what do you see here? How many of these? 1, 2, 3, 4, 12, right?
Yes.
This one, how many? 12. This one? 12. This one? 12. So how many treatments we have? How many treatments?
4 treatments. 12
Anybody
replications.
else got alternative answer? They say we have 4 treatments. How many treatments you have?
4.
4. Are you sure?
Yeah.
How many blocks we have?
4 blocks.
How many replication we have?
12.
Don't look at the color, look at the scenario.
Replicates 12.
Here we have 4 blocks. Block 1, block 2, block 3, block 4. They separate based on section. They do blocking. So in each of the block we have 12 treatment.
12 treatments.
12 treatment here, 12 treatment here, 12 treatment here.
So replicate.
It's just blocking based on the situation. Yeah? See here, maybe this is something is out affecting the plant, the soil here or whatever, light. Here no light coming in the morning, so they decide not to do anything here. They only work here, 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 and here. What you notice is they put everything together, close to each other. Don't do 3 here, another 3 here, and then another 3 here, another 3 here. You are increasing the variability. You must block them together. See here, not necessarily the same shape, but in the same area. Not moving. I'm too far away. Advantages you can read by yourself. Disadvantage also you can read by yourself. I won't ask you an example, so please read. Randomization. I think I already explained, right? You randomize within the randomization is within the block, right? Within the block, you must randomize. Remember the CRD, I think I've seen the picture. CRD, our randomization is just anywhere you can go. Whereas RCPD, we have to make blocks first. Maybe block 1, block 2, block 3, block 4. And then within here randomize. Within there randomize, within there randomize. So randomization should happen within the block. Okay? Each treatment, make sure each treatment occurs once in each block. Okay? Assign the treatments as random to plots within the block. Yeah? Okay. So you can see here, sunlight here, and then here shade. So we have a lot of sunlight here, medium sunlight, low sunlight, and then here we got a lot of shade, less sunlight. So when we want to do blocking, is it horizontal or vertical? Horizontal or vertical? Vertical. So we notice all this thing here is experiencing shade. All these plants here are experiencing shade. All these plants here are experiencing lots of sunlight. Same environment. That's why we block. Who is in the ladies section in the Australia is what? Block. Block C. The one close to the library. Block, right? The one far away there is
Block E.
Which one got light in the morning?
C.
Block A? Any light in the morning? Not much, right? In the evening? Oh, light, nothing, right? There's a variation there. So there is variation. So when we want to block, like in your hostel, you have to block this one against the sun. Somebody says sunblock. Block the sun. Sunblock. You just rub it. So we can see here T1, T2, T3, and T4, right? All the treatments are here. Same thing here, randomize. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Every block. You need to understand this. Because in the test, for example, usually I will ask this. Because if I don't ask this question, it means you have not taken this course. You must learn how to do the design by yourself. Okay, this is the ANOVA 2A. Most of the time you will see only this one. In exceptional case, we have one more here. When I told you we have repetition within the block. Okay. Okay. So formula, if you want to write the formula, it's all there. If you want to remember formula, go ahead. Better you learn how to do it rather than remembering the formula. Okay. So I want to ask a question. Who finished just now last time? Who was the last person?
Me.
Alright. Choose anyone. Izam, choose somebody. Anyone. Anyone? Huh? No, you have to choose. Don't choose. Huh? Who? Awatin. Okay. How many blocks do we have for this experiment? How many blocks do we have? Leave her to answer.
4.
How many blocks?
4.
4. Is it correct?
4 minus 1.
Next person, choose.
Oh.
Next person, choose. Cepat, cepat. You need to choose. You're thinking already.
Nadia.
Nadia? Okay, Nadia? Okay, how many replications do we have for this experiment? We have to answer. How many replications? We are all learning. What is the number of replications? She answered, huh? You're not sure. How many replications? 16. Is it correct? No. You see here, I keep telling you. In block experiment, replication is the same as block.
Oh.
I keep saying many times, in block experiment, replication is the same as block. So this block, some people will write here replication. Okay? So block is the same as replication for block experiment. Okay? Choose somebody. Choose somebody.
Ezron.
Ezron? Ezron? How many experimental units we have total? Total experimental units. Okay, he says 16, correct? Yeah, okay, that's correct. 4 replicates or 4 blocks times 4 treatment equals 16. That's why we have here 16 minus 1 is 4 minus 3 is 4 minus 1 3. 4 minus 1 3. How do you get this answer? So just 15 minus 3 minus 3 give you 9. This plus this plus this will give you the total. So same thing here. After you do all this SS, you have to calculate this one by yourself. Total treatment and block. This one is this number minus this and minus this one will give you this answer. Right? Try your calculator. To get this answer, it is this number minus this two. To get the error message. Correct? Okay. How do you get this number? 8.79. Is divided by 3. To get this number here? 216 divided by 3. This one? Also. Okay. Is divided by 9. Okay. You can try. The more you try, the more you become expert. How do we get this one? Two-way ANOVA. That's why we have two numbers here. Because it's two-way ANOVA. So we have 1 and 2. Block and treatment, or replicate and treatment. So to get this answer is this one divided by the error term. 8.79 divided by 6.64 will give you this answer. And to get this answer, it is this number divided by 6.44. You try. Divide by error. That's why, because this number later, we need to compare with the table. To get the table, this one. So 3 and 9. 3 and 9. For block and treatment, they're the same because this also is 3. If this is 4, then this answer will be different. But because they are both 3 and this is 9, you get the same answer. So reject or accept? Block. Do you reject the block or accept the block? Accept. Okay. Block, accept. Okay. Treatment? Reject. Okay. Anyone here not clear? It's okay. We are here to learn. Huh? Anybody not clear? Don't be shy. No? Ah. Because if you don't say, doctor, can you explain this one? I expect to know. For everybody else. So how do we get this one? Same thing again. I show you how to do. We will do example one by one. Now it's only theory. Remember, we will have our table, 5% table. We have to choose one number here, and then choose another number here. In this case, we have to use 3 and 9, or 3 and 9. So here, 3 and 9. And then if you check the table for 5%, the answer is this one, 3.86. 3.86 somewhere here. 3.86. Now you use that number to draw your F code. Use this number to draw your F code. So make your decision easy. Don't try to remember if F curve is greater than this one. No. This is the easiest way. 3.86. This is our critical point. So this answer here is 1.36. Where is it for? Somewhere here, right? You start here 0, you count, maybe 1.36 is there. So this is acceptance zone. Accept. Anything outside, we reject. So 11.19 is outside, right? Yeah. Somewhere there. So reject that. This one we accept. Block, accept. Means when we accept, what do we mean? Is there any difference? Yeah, no difference. We're all equal. If you are inside the house, we are all equal. If you are inside here, we are all equal. Once you go outside, you are different. That's why we reject you. Once you are outside, this is the pin 2. You are outside of the pin 2, reject. You are inside here, accepted. Once you are accepted, means we are all the same. HO, mean 1 equals mean 2 equals mean 3. How many treatment there? 4. Equals. They are all the same, equal. So we accept that. For the blocks. So is it necessary to do a block experiment for this one? No, it's not necessary. I write from this result, the blocking is useless. No need to do blocking because no difference in the block. Better I do CLD. Why waste my time doing as but we don't know until we do the trial. You remember chicken? You are not here last week, right? Okay, this question is for her. Nobody else say anything. Huh? Please allow her to answer. Or Lukman. Or one more person. What's his name? Right. Only these 3 can answer. One Irene, huh? Okay. Block 1 and experiment 1 or experiment 2. Which one is CRD? You look at the picture. Based on all what I have been talking about. Which one? The picture is more clear here. 1 or 2? Which one is CRD? Allow them to do what this guy. You look at the picture keenly and then give the answer. Take your time. How many types of chicken we have? 4 types. Okay. Is it 4 types of chicken? Okay. How many? If you have 4 types of chicken, how many blocks do you expect? If you have block experiment.
4.
Huh? If you have 4 types of chicken, and they say we have 4 types of chicken, you must 4 types of chicken. The total experimental unit there is what? Total is 20. What do you put here to get 20?
5.
So we know we have 4 applications of 4 blocks now. So the block, can it be vertical or horizontal?
Or vertical.
No, not you. The block can be vertical or horizontal? Are you sure? The block, can it be vertical or horizontal? What is vertical? Vertical this way, right? Horizontal this way. We have 5 blocks. Can you have 5 this way? 1, 2, 3, 4. Where's the last one? Cannot, right? Only this way we can have block. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that is the technique. Where to look? So can you tell? You already know which one is the block. So which one is here? Number 1? She said number 1. Do you agree? No. You said number 2. Okay, we have that also. So which one is correct? 1 or 2? Number 1 is correct. It's a block. Number 2, salah. You can see here. If you remember, in the block, you cannot repeat the treatment. So you see here in this brief, you consider this a block. We have 2 types of the same. Here also we have 2 of the same. Here we have 2 of the same. Cannot. So this is a block. You can see here, this is different from this one, different from this. They are all different. They are all different when you look at every block. Are you clear?
Yeah.
So within the block, you must have all the treatments. Because if you see here, if you consider this, if you want to consider this a block, something missing here. Which one is missing? Black is missing. So you cannot call this a block. Rather, you have 2 of these. This one should come here, this one go there. And then if you put this one also, you already have 2 like not correct. You must have only 1 type. Unless you have replication lab. So are we clear about this design?
Yeah.
Between CRD and RCBD. Okay. We have 5 sources and a control. For example, wanted to apply the results over a wide range of conditions. Salt type is the blocking factor. Location, located 6 plots as random to each other. Okay. Okay. So what was the last one just now?
Nadia.
Nadia? Ezron, choose somebody. Cepat. So we are running out of time. Choose somebody. Choose anybody. Musi? Susie or Musi? Right. How many treatment do we have for this experiment? 4 treatment. Is she correct?
Yeah. Yes.
4 treatment. Are you sure?
No. What 3?
How many treatment?
6.
6. Okay.
Why? Oi,
Block in,
hati-hati.
this is a block. Not
Ada
a
pula
list.
tu hati-hati.
So 6. Replication. Choose somebody.
16. Sama kan replication?
Okay. You have your name.
Agama.
How many replication? 4 replication. Correct or not? We have 4 here, so there are 4 blocks. So 4
Sama
replication.
kan? Blok sama kan?
Okay. How do we get this answer? Choose somebody. Ira? Ira? Okay. How do you get this answer? 17.19. How do you get? Everybody try it. They call not, but you try also. How do we get this answer? 17.19. F calculated for treatment. How do you get it? Okay, this divided by? Correct? Yeah. Okay, one last one. You choose somebody. One last one. Choose somebody. One last one. Choose. Rina. Okay. Rina, how do we get this number? Aaron SS, how do we get this number? Based on the data you have here. How do we get this number? How do we get 44.52? How? Try. You can only get it from here. How do you get this number? Huh? It's Reina supposed to answer, not you. Answer? Oh, yeah, that's why. You must ask in class, Make sure you understand. How do you get this? This is error, huh? So, total minus this will give you this answer. Just because I move the things around, then you get confused. Is that clear? Okay, right. Okay, these are the means if you calculate based on the data. Coefficient of variation 5.6 means good. Okay. Standard error also 1.22 good. Okay, same thing. We will need to report our data later, which we will learn later. And the last but not
Next month.
Sunday.